All right, it looks like the count has stabilized, so just going to go ahead and get started. Hello, everyone, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, both research and operational settings. My name is Alex. I'm here to help coordinate and deliver the webinar, so feel free to please contact us at OSDI if you have any comments or suggestions. We're also taking speaker recommendations if you could send us an email at ufs.modeling@noaa.gov with any recommendations you might have. Due to the high number of attendees, you'll be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, I'm putting a Google Doc in the chat that you can submit your questions, and we'll take care of those at the end for about 15 minutes. Today's webinar is on tropical variability in NOAA's Unified Forecast System, impact of convection and ocean coupling, presented by Dr. Lisa Benson and Maria Kenny. Dr. Lisa Benson is a research scientist at the Physical Sciences Laboratory of NOAA Earth System Research Laboratories in Boulder, Colorado. She leads the model development team in the Model Development and Data Assimilation Division. She joined NOAA ESRL PSL in 2017 and most recently from the research branch of the Swedish Meteorological and Hydrological Institute, SMHI, where she worked between 2006 and 2017. Dr. Bengtson's research is focused on improving operational numerical weather forecasts across a range of scales through the development of physical, stochastic, and deterministic parameterizations, and is actively involved in the development of NOAA's Unified Forecast System. Our next presenter, Dr. Maria Geen, is an associated scientist at the Cooperative Institute for Environmental Research at the University of Colorado Boulder and the NOAA Physical Sciences Laboratory. Before joining CERES, she worked as a postdoctoral fellow in the climate analysis section at the National Center for Academic Research. The research focuses on large-scale tropical convection, its predictability and representation in numerical weather forecasts, and weather forecast error impacts on the U.S. West. She received her PhD in 2012 from New York University in atmospheric ocean science and mathematics. I'm going to go ahead and turn the screen over to Lisa so she can start presenting.
Okay, thank you. Thank you for that introduction.
We can see your slides now.
You can see them. Okay, thank you.
Yeah.
Let me see if I can get the camera to. Oops. Now I lost it, did I? Or did I just? Okay. Maybe. Can you see the screens now?
Yes, we can. Thank you.
Okay, thank you for that introduction. As you said, we're going to speak about tropical variability in the UFS and look at the impact of convection and ocean coupling. And we're going to alternate who's presenting this work. Oops, let's see if I can. Okay. Hide this bar here. Okay, so the motivation for this work is the forthcoming global forecast system, GFS version 17 and GEFS version 13, which is an ensemble component. They will be the first global forecast applications to become operational under the UFS infrastructure. So as such, it will be the first version of the GFS GEFS or fully coupled Earth system models. The GFS version 17 and GEFS version 13 and the upcoming seasonal forecast system version 1, they includes innovations that have been included in so-called coupled prototypes coordinated between NOAA and the community under the UFS Research to Operations project in a stepwise manner. So in this presentation, we'll provide a concise overview of the incremental changes introduced to the cumulus convection parameterization schemes, both shallow and deep, during this prototype phases spanning from GFS version 16 to the forthcoming GFS version 17. With a close eye on variability in the tropics, primarily driven by equatorial waves interacting with moist convective processes. And we'll also share some new diagnostic capabilities developed at PSL to assess tropical variability in the global UFS applications. So this slide is rather busy. I'm not going to go through all the details here, But just to give you an idea of the physics updates that have been introduced into the UFS coupled prototypes during this prototype process. So prototypes 1 through 5, if you look at the left side here, they were using GFS version 15 physics. Then in prototype 6, the GFS version 16 physics suite was introduced. So that was a rather big change in the prototypes, and at that time we also went from 65 levels to 127 levels. So this prototype 6 physics suite includes the NOAA land surface model, the TKE EDMF boundary layer scheme, GFDL cloud microphysics, deep convection from the SAS scheme, scale-aware SAS, shallow convection from the scale-aware mass flux scheme, and radiation from RTMGP gravity wave drag by the unified gravity wave drag version 0. And then throughout the prototype process, there's been incremental changes in physics. And we're right now on something called a high resolution prototype 3. So maybe I'll point out a few examples. In prototype 7, there was an upgrade from NOAA to the NOAA MP land model. That's probably the biggest update in this prototype. Also some additional refinements and tuning in PBL and convection. In prototype 8, the biggest update is probably switching from the GFDL cloud microphysics to Thomson microphysics, and at the time also including some refinements to this Thomson microphysics scheme. We also included the cellular automata convective organization scheme and additional updates through really all the components of the model. After prototype 8, the prototype development was sort of diverged to one for GFS version 17 and another for GEFS version 13. So for GFS version 17, the prototypes are called high resolution prototypes, and we're currently on the 3rd. For the GEFS version 13, they're called ensemble prototypes, but they share a lot of the same physics, all the same physics actually. So in HR1, I think the biggest update is essentially a new closure to convection. And in HR2, there's been more refinements and tuning based on results that we've seen in the preceding prototypes. And lastly, in HR3, there's a new gravity wave drag scheme, something we've been wanting to include for a long time, but it's finally just sort of making its way in. So yeah, I think maybe the only other thing I want to say on this slide is a really huge acknowledgement to all of the UFS developers, in particularly maybe the infrastructure team, just getting the all the code onto GitHub and all the component models, coupling. It's a huge undertaking by a lot of people, and I was thinking to start listing all the people to acknowledge, but I realized quickly that's a slippery slope because there's so many people involved. And I think, yeah, it's a really impressive sort of accomplishment to the entire UFS system. So acknowledgement to everyone involved. So the outline today, Maria is going to talk about tropical diagnostics capabilities and demonstrated using previous versions of the GFS and also the prototypes of GFS version 17 and GEFS version 13. I'm going to speak to the updates we've done to the cumulus convection parameterization. And then we're also taking a first look at some tropical variability in the seasonal forecast system as sort of proof of concept runs. So I will pass it over to Maria.
Thanks, Lisa. Yeah, can you, we lost the slide.
Oh, what happened there? Let me see if I can, there.
Yeah, thanks, can you go? Yeah, so this is work that has had a lot of input from Brandon, Juliana, and George, also at PSL. Can you go to the next slide? So in general, forecast skill in the tropics, especially for precipitation, is not as good as in mid-latitudes. And it's not very well understood which processes in the tropics are most important to mid-latitude forecast skill, although we do know that there are several well-known sources of predictability that go beyond a few days in the tropical atmosphere, such as the MJO and convectively coupled equatorial waves. So we've been working on having evaluation tools that go for tropical convection and tropical variability that go beyond statistical skill scores, in the hopes that having those tools will help us better understand model behavior with respect to tropical convection and help us identify forecast error sources in the tropics related to moisture and convection coupling, convectively coupled equatorial waves, and the MJO. And I'm going to go through some of these evaluation tools, and I'm going to use several versions of the UFS and GFS version 16 and 15 as examples. Next slide, please. So the runs I'm going to be looking at is for GFS version 15 and 16, some parallel runs and operational runs respectively for in the summer of 2020, and then for the coupled prototypes, all 168 initializations. And then I'm also going to show some results comparing HR2 to GFS version 16 for those runs. Next slide, please. So the first diagnostic I like to look at are these Hoffmuller diagrams where the y-axis is dates, time increases going down, and then two versions of the truth year 5 and I-merge, and then forecast hour 6 for both GFS version 15 and GFS version 16. And you can see these zonally propagating precipitation anomalies, which at forecast hour 6, the models are very good at picking up that variability. So what this does is it helps us assess the zonal propagation of convective features in the tropics, and then the pattern correlation between the forecast and the truth can be used as a skill score. Next slide, please. And here I'm showing that for HR2 and GFS version 16. And it's a fairly small sample size, so it's pretty noisy, as you can see. And you can see that all the changes that have been made to get to HR2 mean for this particular diagnostic that the correlation skill actually improves by about 0.15 at forecast hour 6 over GFS version 16, which is a very big improvement. And it's actually even above the skill that you can see when you compare error 5 to I-merge at forecast hour 6. And then that also means that the skill correlation stays above 0.5 for the first 3 days instead of the first 1.5 days when we're verifying against error 5. And then this skill improvement is consistent for HR2 until, about for the first 3 days into the forecast. Next slide, please. Another thing to look at in the tropics are these space-time spectra, where you're looking at zonal wave number versus frequency. And what this helps us look at is how well do models initialize and propagate convectively coupled equatorial waves. And then looking at space-time coherence spectra rather than power spectra, we can see regions in space-time that have enhanced coupling in the tropical variability between, for example, precipitation and dynamical variables, without having to estimate a background spectrum and remove that. So with these, we can evaluate the precipitation dynamics relationship strength and how it changes with lead time. And what these panels on the right here show is that for GFS version 15 and 16, as you're going from lead time 6 hours to 48 hours, the strength of the coupling, so the strength of the coherence between precipitation and divergence at 850, so low level convergence, decreases pretty rapidly. Can you go to the next slide, please? Oh yeah, and I already said this, so we can skip this one. So during the model development process, you can also use these. And what I'm showing here are, again, space-time coherence spectra, and this time the top row is for several of the UFS prototypes prototype 5, 7, and 8. And then on the bottom, ERA 5 iMerge, and then also the EC S2S model from the 2021 version. And go next slide, please. So you can see that compared to observations in the EC model, there's the band of coherence is a little too narrow in wave number. And then next slide. In the UFS prototype 5, the coupling is too weak. You get a little bit more spread, and a little bit more dispersion, which is nice, but it's too weak compared to observations. Next slide. Yeah, no, that was good. Going to prototype 7, the coupling gets a little bit stronger, and then going to prototype 8, the coupling gets even stronger, and you end up with more dispersion. So all of the changes that were being made between those prototypes, we're going in the right direction when you're looking at this metric. Next slide, please. And Lisa, do you want to talk about this, or I can keep going if you like?
Yeah, I could just mention that during this process, we looked at different specific physics updates between prototype 7 and prototype 8. One of them was the inclusion of the cellular automata convective organization scheme. And so we reran a set of prototype 8, turning this CA off just to look at the impact of this coherence spectra. And I think our conclusion was a bit inconclusive, that it was it's a small enhancement in coherence, but perhaps at too high frequencies. And I guess it doesn't explain all of the differences that Maria showed on the previous slide, going from prototype 7 to prototype 8. I think maybe one result that you had shown before was that this coherence is generally for earlier lead times. And I think one of the updates going into prototype 8 was the update to spin up land initial conditions, and I think had actually a pretty large impact on initiation of convection. So that may be another reason for the enhanced coherence between P7 and P8. And the third one is a change in the cloud microphysics from GFDL to Thomson, but we haven't isolated that one with the coherence spectra yet. So I'll pass it back to you.
Yeah, thanks. Yeah, I guess in general, you can say that it's just, we know all of those changes together make a big difference, but it's hard to untangle exactly what each of those changes, what the impact is of each of those changes, because there's just too many of them. So the last tool I wanted to show some results from is just looking at convectively coupled equatorial wave activity and skill. And essentially what we're doing is we have UFs that are based on observed filter precipitation, and we can take the model precipitation at each forecast hour, project onto these UF patterns, and compute a wave activity index. And then to get a skill score for that, or skill correlation, we can compute the anomaly correlation between the observed and the model activity index. So looking at just GFS version 16 versus 15, overall GFS 16 was a small improvement over GFS version 15 for the equatorial Rossby waves and the MJO. But it was the time period I was looking at for these experiment was a little short, and the Kelvin wave skill was not very good. Next slide, please. So now looking at this for the HR2 experiments, and I combined both the winter and the summer runs into one here, even though I'm just showing an example of the activity time series for December here. Overall, HR2 skill is higher than GFS version 16 in this evaluation tool. The sample size, again, is fairly small, so you can see that the confidence intervals are pretty large, but overall the blue curve tends to be above the orange curve. And what's even more interesting in terms of the MJO here, the skill actually stays above 0.5 for several days. and we have a big improvement in the Kelvin wave scale. Next slide, please. So just a quick intermediate summary here. So we consider skill metrics for tropical convection, and in particular for convectively coupled equatorial waves. We know that much precipitation skill in the tropics is lost immediately in the hours following initialization. In the coupled prototypes, the coupling between convection and the circulation is improved in terms of the scales that it happens at and the strength, but it still decreases rapidly with lead time. HR2 is definitely an improvement in these precipitation-based convectively coupled equatorial wave skill metrics over GFS version 16. And we're going to show a little bit more at the end here, I think. And so because we got some similar results for the coupled prototypes, we hypothesized that the coupling between atmosphere and ocean might be beneficial to this result. And several of these diagnostics are included in last year's November release of METPlotPy and METCalPy of MET+, which hopefully will be useful in the future once the evaluation for the operational runs switches over to being MET+ based. So hopefully it'll be easier to actually look at this in operational runs. Back to you, Lisa. Thank you.
Okay, thank you. So next, I'm going to present the updates, a more concise overview of the updates to the cumulus convection parameterization between GFS version 16 and GFS version 17 at the up to the high resolution prototype 3. So I would like to, this is work I've been doing together with Jean-Gil Han and EMC. And I would also like to acknowledge Wei Li and Fenglin Yang at EMC and Maria Gene and Juliana Diaz at PSL. So here's a list of summary of the updates to cumulus convection throughout the prototype process. The first update was implementation of a positive definite mass flux scheme and a method for removing negative tracers. This was motivated by the fact that when we introduced Thomson into prototype 8, we found that, well, essentially the Thomson scheme sets all negative tracers coming into the scheme to 0. And in a global system, this adds mass over time. So there was some work at EMC to try to identify why we have negative tracers coming out of the PBL and convection schemes, and finding a method to alleviate that. So this led to this development of this positive definite mass flux scheme, and then also a correction for negative tracers, sort of using a borrowing method. The next update is introduction of a new cumulus closure. This is based on a prognostic evolution of the convective uplift area fraction. And this new closure is introduced both to the shallow and deep convection scheme. The motivation for this work is the SAS scheme is based on ideas from the sort of really took place when we have convection on really, really large grid boxes and very long time steps. So you can assume that convection is sort of statistical equilibrium with a large scale flow, and the time step is large enough that the convection occurs within a time step. When you go to higher resolution and shorter time step, the assumption of negligible area fraction is invalid any longer, and also evolution can sort of take place over several time steps. So this is what motivated the work with this prognostic closure. In addition, we introduced 3D effects of cold pool dynamics and stochastic initiation using the self-organizing cellular automaton. The idea here is that convection is very much a 3D process, but physics we do within our modeling systems in general is column-based. So the cellular automata can initiate convection in a nearby environment through some stochastic self-organizing movement of cells, I should say. The last 3 items on this list were motivated by either biases that were seen in GFS version 16 or alternatively biases seen within the prototype process. So the first one is an introduction of environmental wind shear and TKE dependence in convection. And this was motivated by some biases seen in the hurricane forecast, in particular intensity of storms. There's an introduction of a stricter convective initiation criteria to allow for more CAPE to build up, and then to address a low CAPE bias that was seen in GFS version 16. I should mention that not only convection is what is what influences the amount of CAPE, and other updates to boundary layer and surface has also been introduced to try to alleviate this low CAPE bias. And finally, there's a reduction of convective rain evaporation rate to address a systematic cold bias near the surface in GFS version 16. These updates or innovations have been published and individually looked at its impact within the prototype process. But in this study here, I am looking at the combined effect. So in order to do that, I started with the HR2 prototype. Those are at C768, which is roughly 13 kilometers. So the control is the control HR2 prototype. This was run by EMC. And the experiment that I call V16Conv is HR2, but I revert all these changes that I just listed on the previous slide. So I'm at the level of GFS version 16 cumulus convection. So I ran a summer period and then also ran a couple case studies a little bit longer to take a look at tropical variability in the MGO. I want to mention that many of these physics updates since GFS version 16 have been done sort of in tandem with other updates, primarily in clouds, radiation, and boundary layer. So reverting only convection could potentially provide some unexpected results. Here's a look at the tropical cold bias that we see. So the black line is our HR2, and the red line is HR2, but with convection from GFS version 16. So you can see that in general, as with increasing lead time, the atmosphere warms up in the GFS, and the impact of the convection is a warming. So it does alleviate the bias somewhat, but there's still a cold bias. And I think in assessing some of these results, they're all cold started in the atmosphere from GFS version 16. So they start off cold. And I think we have some challenges ahead when we start cycling these runs, since we see that it is a warming over time. And we know that we're starting off with a cold bias in the tropics. Here's the specific humidity profiles. They are dry, which we know in the tropics, and the updates to cumulus convection seen in black curves are helping to alleviate that lower troposphere dry bias to some extent. Actually, at the 96-hour forecast lead, we're somewhat warm. Somewhat moist in this case, which again maybe it's gonna be challenging when we start cycling these experiments, when we don't start from a state that's already dry. Perhaps we have to make some additional changes within the convection to address that. This is the CAPE. So basically the left panel here shows a CAPE, and this is the HR2 minus the V16Conv experiment at early forecast times, and this second panel is at later forecast times. So you can see a kind of similar story. We do see enhancement of CAPE in the tropics, and this enhancement is larger at later lead times. Something we did notice is that over CONUS, it actually looks like in some areas there's a little bit of a reduction in CAPE, and we're looking into to see if there's some change in convection. For instance, a reduction of convective rain evaporation, or something that would have reduced the amount of CAPE. I think it could also be a sampling issue if storms move, because we have some points with an enhancement, so it's not as clear. But over the tropics, it's clear that these changes have led to an enhancement in CAPE. Next, I look at the CONUS precipitation. This is the bias score, and this is the equitable threat score. This is when we have the V16 version of convection, and this is the HR2. In the bias score, a value of 1 is the best. So in general, the GFS version 17 update to convection is an improvement compared to the GFS version 16 convection. You can see that by kind of having some softer colors in the HR2 panel. This one shows the difference between HR2 and the version with V16 column. So the ETS score is generally, you can see more green, which is also associated with an improvement in the ETS score. Here I also include some uncertainty bars. So let's see, so this is the ETS score, this is the bias score, and these are for early lead times. And in particular in the bias score, you can see like the version HR2 is closer to 1, and in some thresholds also statistically significant. And I think in general, even at longer lead times, you see the same direction, but perhaps not statistically significant at that point due to the small sample. The anomaly correlation, this is the 500 hectopascal height anomaly correlation. It's generally not really impacted by the changes to cumulus convection. This panel is for the northern hemisphere, and this panel is for the southern hemisphere. If anything, it seems to be neutral, but a slight improvement in the northern hemisphere, and perhaps statistically significant at a few forecast hours, and then somewhat of a degradation in the southern hemisphere, but not statistically significant. I think my main conclusion here is that the impact on anomaly correlation is rather small. These are from Maria's tropical diagnostic package, this precipitation power spectra. If we compare the HR2 to the version that has GFS version 16 convection, we do in general see more precipitation power at higher frequencies, and also perhaps enhanced over the sort of tropical depression, or even like hurricane region, somewhat closer to the I-merge precipitation. The spectra are rather noisy due to the short period. Maybe you could say that there's a little bit more power also in the Kelvin band, but it's still a lot less than what we see in I-merge. So even though we saw some improvement in the Kelvin score in HR2 compared to GFS version 16, I think there's still perhaps even more improvement that can be made. This is a look at the MJO. So if we focus first on the top panel, this is the ROMI index, and this is the RMMI index. The ROMI index is mainly based on OLR and says a little bit more about convection and its impact on the MJO, whereas the RMMI index is highly influenced by the winds and says a little bit more about the circulation impact for the MJO. And then the yellow line here is the HR2, and the green is HR2 with a V16 convection. And I think in general, for both these scores, we found that the MJO propagation and amplitude is pretty good. And we found also that the impact of our convection updates was rather small. When we discussed it, we looked at these results and we thought, you know, in our previous work, we've seen that these changes to convection had a pretty big impact on these metrics. And we were speculating that perhaps it's related to the fact that now we're running couple, whereas at the development time we were running atmosphere only simulation. So I also ran these uncoupled to the ocean. And you can see a couple of things. One is that in general, the impact of the ocean coupling seems to be slightly lower amplitude in both the RMI and RMMI, if you compare these two, for instance. And you can also see that the impact of convection matters more when you run uncoupled. And this I've found is a rather interesting result, and also that it poses some challenges for development of convection in these big systems. We often use single column models, we use atmosphere only simulation, and it's rather expensive to run the fully coupled systems. But the response on convection from the ocean is clearly rather different. So it poses some challenges in the development process and transition to operation, I think. You can see here the Hohmöller diagrams, and these look a bit smoother than the ones Maria showed, at least because they are large-scale filtered using Gaussian filter for the MJO signal. This is from Juliana Diaz at PSL. And we see from the iMerge observation and two runs with the HR2, the uncoupled has a much lower amplitude in precipitation, and also there's more eastward propagation when we have a coupled. I think it's rather interesting the impact of the ocean coupling on these convectively coupled equatorial waves. Okay, I think I'm going to pass it back to Maria and look at a little bit more at the seasonal forecast system.
Okay, thanks, Lisa. So yeah, these are the proof of concept seasonal forecast system runs, and I want to acknowledge Phil Pigeon, Xiaowei Quan, Stefan Tulig, and Yan Wang for producing these runs. And can you go to the next slide? So these are Xiaowei and Phil ran a 5-member ensemble initialized on October 1st for 30 years, seasonal runs. And I think this SFS is what they were running is based on the P8 model tag, but it's run at C96, so about 1 degree resolution. What I'm showing here are the precipitation power spectra divided by an estimate of the background, so that all you see is the peaks and the precipitation power. So the first thing, just as Lisa was just mentioning a couple slides ago, is what you can see is that there's very active tropical depression type disturbances in these SFS runs. There's very good convectively coupled equatorial Kelvin wave power. But if you look at the total precipitation spectra rather than this power divided by the background, you see that overall total precipitation variance in the SFS runs is still lower than what's observed. And one little thing to note, since these are long runs, so we can actually look at the MJO power spectra, is that it looks like there's actually a peak in precipitation power in the MJO region down here, wave number 1 and 2, and about 40 days. Next slide, please. For these same runs, we can look at, again, the coherent spectra between precipitation and low-level convergence. Again, you can see these tropical depression types popping out as being coupled between low-level convergence and precipitation. The coupling in the convectively coupled Kelvin wave band is also pretty strong, but not as strong as, for example, in ERA 5. And then again, in the MJO band, you also see some coupling between precipitation and low-level divergence. But one thing that you can see, and that is also pretty common in these, when you compute these from models rather than observations, is that you get a continuum of coherence between the MJO and the Kelvin wave bands, where the model, potentially one of the hypotheses is that the model essentially doesn't actually produce an MJO, but rather a very slow Kelvin wave. Next slide, please. So one example I wanted to show here, this is again for the OLR-based or MJO index, the ROMI. On the left are 2 cases where I show all the ensemble members for 2 different initializations, and on the right is the respective ensemble mean. And what I thought was actually very nice is that the SFS is able to propagate the MJO, or at least the MJO related OLR signal, for multiple weeks in some cases. And one of the issues that models tend to have is that propagating the convective signal associated with the MJO through the maritime continent tends to be very hard. But in the SFS, again, we think it's probably related to the ocean coupling. The SFS is actually able to propagate through the maritime continent in some cases. Next slide, please. So these are runs done by Stefan Tulig and Yan Wang, and these are shorter runs again, but again running at C96, so fairly low resolution. And just focus on the yellow and the red curves, which is the free uncoupled run and the free coupled run. And on the left, I'm showing RMM phase diagrams, and on the right, I'm showing the ROMI phase diagrams. And what we can see is that, again, the coupling to the ocean does have a large impact, especially on the convective signal of the MJO, as you can see on the right. And then on the left, on some, and maybe not as consistent, but also has an impact on the wind, the circulation part of the MJO. And usually an improvement, as far as we can tell from the few cases that we've looked at so far. Next slide, please. I think this is you, Lisa.
Oh, okay. So yeah, a brief summary. The tropical variability package that Maria presented is available on GitHub, and some aspects have been added to MetPlus. So this is the address posted right here. There's a manuscript that's been submitted to Weather and Forecasting by myself and Jean-Gil Han, describing these changes in cumulus convection in the prototype process. These updates have led to improvements in reducing temperature and humidity biases, increasing CAPE, and enhancing precipitation power spectra. Evaluation of the MJO reveals different response in cumulus convection parameterization changes, depending on if the model is run coupled to the ocean or uncoupled. And early seasonal forecast system simulations suggest that the C96 resolution is about 100 kilometers, very sensitive to ocean coupling. And I think we need to understand the poor C96 uncoupled results a little bit better. We have seen, and within the SFS project, we've seen other runs, for instance, medium range weather forecast verification suggesting that the C96 uncoupled is really a lot poorer than all of the other configurations. So maybe we shouldn't put too much weight on these results, just rather trying to understand exactly what's going on there. But those are the the SFS is sort of very early on its development path. So with that, I think, yeah, we're happy to take any questions.
Thank you, Lisa and Maria. I'm going to post this document again in the chat for everybody, and then I'll share it on my screen. The document's available in the chat, and then I also have it on the screen here. And it looks like we've only got one item that says, this is not a question or a comment, but an advertisement. We are conducting a user survey for NOAA's global forecast systems in order to implement user needs in terms of requirements. And then it has two survey links, so if you are interested in that.
Thanks, YJ. It's good. It seems that everything is crystal clear.
Yeah, I'll give it just another minute or two, and if we don't have any questions, we can go ahead and end early. Sounds good. Thanks again so much, Lisa and Maria, and we'll send out an email about the next upcoming webinar. Thanks, everyone.
Thank you.
Thank you.